Hi everyone, we are from Group 9 and today we would like to present about our group project, Numbering Methods Group Assignment 2. Right. In today's presentation, we will divide our topic in our presentation into 5 parts, in which is introduction, case of studies, calculation, result and discussion, and also the last one is conclusion and recommendation. Our group consists of 4 members, in which I'm Bengkelek and also Gokai Seng, Wanu AFIQAH, BINTI RAHIMI, and also the last one is Yikisu. Alright, now I would like to present about for the introduction. Okay, in our study case, we have determined the 5 real-world problem that could be solved by using the numbering method, in which is determine in performance characteristic of diesel engine, depths of submersible underwater system, heat transfer estimation, thermistor as temperature measuring device, and also the temperature drop of sea due to evaporation. From the 5 studies, we have chosen the temperature drop of sea due to the evaporation as our studies. So, what is temperature drop? Temperature drop, as known as the temperature decline, may occur as a result of various reasons such as evaporations. Then, what is evaporation? Evaporation is the form of vaporization that happens at the surface of the liquid during its transition to the gas phase. So, as you can see from the picture, this is the example of evaporations of the liquids to the gas surface. So, to calculate or to deeply study the temperature drop of the sea due to the evaporation by using the numerical methods, first we need to consider we need to find information about these studies. For example, such as the relative humidity, saturated pressure, and also the air temperature above the sea levels. After finding these informations, we can use the numerical methods which we study at chapter 4 or topic 4 which is interpolations, to determine the temperature drops of the sea due to the evaporations. Alright, next.
My name is Yikisu. We will present about the case of study. We choose the case study, which is the temperature drop. We will use an interpolated polynomial to determine the saturation temperature for various relative humidity values and compare it to the actual value using the given thermodynamic calculator and the table. In our case study, we choose to use the sea condition of Kuching, Sarawak to create a realistic scene. We use data to determine relative humidity based on the weather and climate in Santubong, Sarawak, Malaysia. First, we will calculate the average annual maximum temperature as our data for calculation by using the graph to show the mean, minimum, and maximum temperature in Santubong, Malaysia over the year. After the calculation, we know that the average temperature equal to 31 degrees Celsius. We can get the saturated pressure for table A4 in the thermodynamic as shown in below. We can get the actual value of saturated pressure in kilopascal when the temperature is 31 degrees Celsius, which was 4.4969 kilopascal. We choose to find the relative humidity with 50%, 83%, and 100% by using the formula. The relative humidity in the formula should divide by 100, and we will get the value for relative humidity with 50% equal to 2.24845 kilopascal, 83% equal to 3.73243 kilopascal, and 100% equal to 4.4969 kilopascal. We can use the calculator for saturated steam table by pressure for 50% relative humidity, and finally get the value for temperature equal to 19.3627 degrees Celsius. The temperature for 83% relative humidity is 27.7707 degrees Celsius. The temperature for the 100% relative humidity equal to 31.0011 degrees Celsius.
Assalamualaikum and hi, my name is AFIQAH BINTI RAHIMI and my metric number is CD190241. Now I will proceed to calculation part. Assalamualaikum and hi, my name is AFIQAH BINTI RAHIMI and my metric number is CD190241. Today I will present my part, which is calculation in order to obtain the temperature drop by using the first order or linear approximation Lagrange interpolating polynomial method. So to calculate the value of pressure at 31 kilopascal, we use 2 points, which is 30 and 35, and using the formula of S minus S1 over S0 minus S1 times F0 plus S minus S0 over S1 minus S0 times F1. Okay. So we insert the value into this calculation, into this equation, then we get the saturated pressure value, which is 4.5233 kilopascal. Then using the value of saturated pressure that we obtained before, which is 4.5233 kilopascal, we use it to calculate the value of pressure at V2, which is we get it as 2.2617 kilopascal. And to obtain the relative humidity of 50%, we need to use the value between 2.0 to 2.5. Using the same formula, we can use the formula to calculate the value of temperature 1 at 2.2617 kilopascal. Then we get the value of 19.3703. Then after obtaining the value of temperature 1, we can use the value of actual minus approximation value, which is 19.3627 minus 19.3703 to obtain the value of error. Then we can get the value of error is 0.76%. And using the same formula and step, we can calculate the temperature drop at relative humidity of 83%. We can use 0.83 times 4.5233 kilopascal. Then we can get the value of pressure is 3.7543 kilopascal. Then we use the 2 point, which is between 3.0 to 4.0. By using the same formula, we can calculate the value of temperature 2 at the point of 3.7543, and we can get the value of temperature 2, which is 27.7621. Then using the value of actual minus value of approximation, which is 27.7701 minus 27.7621, we can obtain the value of error, which is 0.80%. We use linear approximation approach to calculate the value of temperature drop at relative humidity at 100%. Then we need to multiply the value of 1.00 times 4.5233 kilopascal to obtain the value of saturated pressure, which is we get 4.5233 kilopascal. Then we use the value between 4.0 to 5.0. Then we use the formula of linear approximation Lagrange interpolating polynomial method to calculate the value of T3, and we get the value of temperature, which is 31.0097. Then we can calculate the value of error by minus the value of 31.0011 minus 31.0097. Then we get the value of error is 0.86%. We are proving the value that we obtained before by using the FreeMath software. Then we get the value of saturated pressure at 4.5233 kilopascal. Also, by using FreeMat software, we can calculate the value of temperature 1 at 50% relative humidity. Then we get the same answer. Also, we calculate the value of T2 at 83% of relative humidity, and is proved by using FreeMat also. The value of temperature 3 that we calculate before for 100% of relative humidity is proved by using FreeMat software.
Hi, my name is Goh Kai Sen, and now I will present about the quadratic second order language interpolating polynomial method. We sub the x and fx value inside to the formula. When the x equal to 31, we can get the saturated pressure equal to 4.4934 kPa. For the relative humidity 50%, we can get the PV equal to 2.2467. We sub the 2.2467 inside to the formula. After that, we can get the final answer, which the temperature 1 equal to 19.3745. For the percentage of the error, we can get 1.18%. For the relative humidity at 83%, we can get the PV equal to 3.7295. We sub the 3.7295 inside to the formula. We will get to the final answer, which the temperature 2 equal to 27.7885. For the percentage of the error, the percentage of the error equal to 1.184. For the relative humidity 100%, the PV equal to 4.4934. We sub the 4.4934 inside to the formula. Then we will get the final answer, which the temperature T equal to 31.0139. For the percentage of the error equal to 1.25%. We using the FreeMat to prove the saturated pressure. We prove the saturated pressure with a relative humidity of 50% by using FreeMat. We also use a FreeMat to prove the saturated pressure with relative humidity 83%. For the relative humidity 100%, we also use the FreeMat to prove.
For cubic third order Lagrange interpolating polynomial method, we can list out the value of S and Fs, and we insert the value into the formula. Finally, we can get the value equal to 4.4973, which is the saturated pressure when S equal to 31. We'll find the value of temperature for relative humidity equal to 50%. We also insert the value of S into this formula. We will get the final answer of P3 equal to 19.3692. So the temperature equal to 19.3692, and the error is the actual value minus our calculated value, and find the error equal to 0.65%. We find the value of temperature for relative humidity equal to 83%. We also insert the value of S into this formula. Finally, we will get the final value equal to 27.7782. So our temperature equal to 27.7782 degrees Celsius, and our error equal to actual value minus our calculated value. So our error is equal to 0.81%. We find the temperature for relative humidity equal to 100%. We also insert the value of S into this formula. So we will get the final answer equal to 30.9892. So our temperature is equal to 30.9892 degrees Celsius, and the percentage of error is equal to actual value minus our calculated value, and last, the error equal to 1.19%. We're using the FreeMat to prove that our calculated saturated pressure is correct. We're also using FreeMat to prove that our temperature is correct with relative humidity of 50%. the proof of Riemann for relative humidity equal to 83%. This is the proof of Riemann to calculate the temperature with relative humidity of 100%.
Finding the temperature drop by using the Newton divided differential interpolation collecting polynomial method, which we learned in numerical method. So when the air temperature is 31 degrees Celsius, so we need to find the saturated pressure first. So as you can see from the table from thermodynamics, there are no 31 degrees Celsius, so we need to using the Newton divided difference interpolating polynomial to finding the saturated pressure at 31 degrees Celsius. So by using the temperature drop, we need to using the we create a table. So a table like this. So there are four orders, so first order, second order, third order, and fourth order. So to calculate the we are giving one example to calculate like 0.21542. How to calculate this one is by using the interpolations. So meaning that's 4.2469 minus 3.1698 divided by 30 minus 25. We're getting this one. Then corresponding we calculate until the fourth order. After we construct this table, next we're using the formula. So 3.169 is here, then plus 0.21542 is here. Then we need to time x minus 25. Then we continue 0.0061 time x minus 25, x minus 30. Then continue by we using this the top value, so 3.16, 0.214, 0.061, and also 0.0098. Then we time the corresponding. For example, we'll get this formula. After we getting this formula, we'll substitute the temperature we want. So it means that the temperature we want to calculate is 31 degrees. So we sub the 31 degree into the x value. So at the end we'll get when the temperature is 31, the saturated pressure will be 4.4954 kilopascal. Okay, after calculating the saturated pressure at 31 degrees, now you need to calculate the saturated pressure corresponding to the relative humidities. For example, 50%, 83%, and also 100%. So we'll get the 4.4954 kilopascal that we get. Then we time the relative humidity. For example, 50% we time 0.5, 83 we time 0.83, and also 100 we time 1. So we'll get the saturated pressure according to the relative humidity. So like PV1 is 2.2477, PV2 is 3.7312 kilopascal, and also the last one 100 humidities, because we time 1, so we'll get the same 4.4954. Okay. Next, after calculating the saturated pressure, now we're using the saturated pressure according to the relative humidity to calculate what is the saturated pressure at that saturated pressure value. Okay. Next, we are also using the thermodynamics table to calculate the saturated temperature. So the figures below shows the Newton divider interpolating polynomials calculation method. So for example here, for first order how to calculate, second order how to calculate, and also third order how to calculate. Alright, now we will find the saturated temperature at T1 first. So when the relative humidity is 50%, and also the saturated pressure just now we calculate from 50%, we get 2.2477. So we also construct the table from, because the PV is in between 2.2477, we'll construct the table. Then also we'll after constructing the table, calculated the first order, second order, third order, fourth order, we can get the Newton interpolating divided difference polynomial formula. So for example 6.9696, then plus 12.1002 then this one is x minus 1. So plus also from the top negative 3.149 time x minus 1 and x minus 1.5, and continue where we get the full formula. Next, the temperature we need to calculate is when the PV is equal to 2.2477, right? So we just substitute the 2.2477 inside the Newton interpolating divider difference polynomial formula that we get. So at the end, we will get the T1 is equal to 19.3533 degrees Celsius when the relative humidity is 50%. Okay, next we will find the saturated temperature T2 when the relative humidity is 83%. So when relative humidity is 83%, we can get PV2 is 3.7312 kilopascal. So at the same, we're using the same method. We construct the table to find the first order, second order, third order, and fourth order. Then we put the value inside the table. Then we construct the Newton interpolating divider difference polynomial formula. So means that 13.0197 plus here is 8.912 times x minus 1.5. Then we plus negative 1.7866 times x minus 1.5, x minus 2. Then continue, we'll get the full formula. Next, we need to find the saturated temperature when the PV is equal to 3.7312, right? So we substitute the 3.7312 into the x. Then after calculating, we get T2 is 27.7822 degree Celsius. Alright, next, for the saturated temperature when the relative humidity is 100%, which means the PV is equal to 4.4952 kilopascal. We're using the table to find the first order, second order, third order, and fourth order. Then we substitute the we create the Newton interpolating divider difference polynomial formula. So we're getting like 17.4953 plus 7.1646 times x minus 2. Then we plus negative 1.16 times x minus 2, then x minus 2.5. Then continue until the last one is negative 0.03324. Then we need to x minus 2, x minus 2.5, x minus 3, and also x minus 4. So this is the formula. Then when we want to calculating the saturated temperature when PV is equal to 4.4954, right? So we substitute the 4.4954 into the x value. So get the formulas as from below. After we calculating, we get the T3 is equal to 31.0066 degree Celsius. Okay, after calculating the temperature, saturated temperature for T1, T2, and T3, now we like to calculate the errors as compared to the actual saturated temperature value. So we will get 19.3627 minus the T1 that we get from the by using the Newton interpolating divider difference polynomial method. So we'll get the error is equal to 0.94%. For the relative humidity 83%, for the T2 is equal to 27.7822. The errors that we get is 1.21%. And the last one, when the relative humidity is 100%, the T3 is 31.0066. So the errors that we get is 0.55%. So the errors is a little bit bigger for relative humidities for both 50, 83, and 100%. This may due to the decimal places that we get we calculate when we construct the table or for first order, second order, third order, and fourth order. So it is recommended to get even more decimal places or value after the decimal places to get the even more accurate answer. Next, we'll use the free method to prove our answer by using the Newton divider difference interpolating polynomial method that we're using. So for saturated pressure, what we're getting for manual calculation, we get is 4.4954. But from the free method that we get, the answer is 4.4934 kilopascal. So they are a bit different, maybe due to the decimal places. Alright. Next, we will move on to the T1. Temperature 1 is 90.3533. From the free method, by using the free method, we're getting the answer is 19.3535. There are 0.00032 of value difference. So for T2 is, when T2 is 27.7822, the answer that we get or proof from the free method is exactly the same as 27.7822. Okay. Next, move on to the last one is T3 is 31.0066 degrees Celsius. So from free method, we're also getting the answer is 31.0066. Alright, that's all from me. Thank you.
Now we are moving to the next part, which is results and discussion. The table shows the value of approximate vapor pressure for method, which is linear approximation method, second order method, third order method, and Newton's divided difference method. And we compare the value of approximated vapor pressure with actual vapor pressure for different value of relative humidity at 50%, 83%, and 100%. The second table shows the comparison of approximate temperature by using different interpolation method. Using the same method, which is linear approximation, second order method, third order method, and Newton's divided difference method. And we compare the value of approximate with actual temperature for different value of relative humidity. For each point of relative humidity, we can see that every method shows the different value of error. And this table shows the value of comparison of errors by using different interpolation method. We also make a comparison between a manual calculation value and simulation works using free method software. And you can see that linear approximation method, quadratic second order method, cubic third order method, and also Newton's divided difference method is compared to the value of free method software. The final table shows the comparison between manual calculation and simulation works using free method software. And we can see there is a different value and also there is a same value in this table. From the results, we can see that the approximate value that we calculate using different interpolation methods give similar answer to the actual value. For example, for approximated temperature when humidity was 50%, the range of approximated answer was in between 19.3553 degrees Celsius to 19.3745 degrees Celsius, compared to the actual value of 19.3627 degrees Celsius. This shows that using cubic or third order Lagrange interpolating polynomial give the highest accuracy with 0.650% of absolute error. Besides, when humidity increased to 100%, Newton's divided difference method showed the highest accuracy of 0.55% absolute error compared to other Lagrange interpolating polynomial method. All of the four methods, which is linear approximation method, quadratic Lagrange interpolating polynomial method, cubic Lagrange interpolating polynomial method, and also Newton's divided difference interpolating polynomial method can be used to calculate vapor pressure and temperature because the error of each method are below than 1% and it is acceptable. We found a slightly different value for Newton's divided difference method compared with manual calculation and simulation work by free method software. and it happened on both calculation for vapor pressure and approximate temperature. The highest different value is relative humidity with a 0.0018 value difference, and this may due to the decimal places that we took for manual calculation was not same as pre-made software. The difference in value for approximate vapor pressure was when using Newton's divided difference method with a 0.002 value difference.
In a conclusion, interpolation is a method to calculate a new data within a given data range. Okay, by using this method, we can get a higher accuracy. Okay, besides, we also found that we can get even higher accuracy by using the qubit third order ligation interpolating polynomial method and the Newton divided difference. We can estimate the value of approximate vapor pressure and the approximate temperature for our case study. Okay, we also can compare our manual calculation and use the simulation work for pre-made software. We found that some of the value different compared to the pre-made software and the actual value when we conducting this study. Okay, this effect may affect the accuracy of the answer. Therefore, we also recommend that when using the manual calculation, we advise to use the more decimal place as possible to increase the accuracy of the result. Last, thank you for watching our presentation video. Thank you.